In this video, I will explain how a floating point value is represented in computer's memory. You might need to be familiar with the excess k notation to follow this video. If you are not familiar with the excess k or bias k notation, please watch another video in this series. It is the one entitled How Computer Represent Integers, the one with bias k excess k notation. Representing floating point numbers is a little bit more complex than representing integers. In computers, the binary format of a floating point number is divided into three parts: the sign bit, the exponent, and the fraction. In IEEE 754, which is an industry standard for representing floating point numbers in computers, a single precision floating point number is represented in 32 bits, in which the most significant bit is the sign bit. The next 8 bits serve as the exponent, which is the bit pattern of an integer represented in excess 127, and the rest 23 bits serve as the fraction. For double precision floating point number, 64 bits are used. The first one is the sign bit. The exponent part takes 11 bits, and the rest 52 bits serve as the fraction. Like its name suggests, the sign bit determines the sign. It lets us know whether the number is a positive number or a negative number. It is 0 for the non-negative number, while it is 1 for negative numbers. The tricky parts are the exponent and fraction. This is how we extract the two parts. First, we write the floating point number in base 2. Then we shift things around a little bit to obtain the same number in the scientific format, which is 1 point something times 2 raised to the power of n. The power of 2 is the exponent part, and the floating point of the first number serves as the fraction. Let's look at an example. We are trying to convert 0.34375. This number is 2 raised to the power of minus 2 plus 2 raised to the power of minus 4 plus 2 raised to the power of minus 5, which we can write in binary format as 0.01011 base 2. Now, we will shift the decimal points so that this is in this format. Therefore, we obtain. Look at 1.011. Take only the fraction part, which is 0.011. Put that in the fraction part. And also, since this one is a positive number, use the sign bit as 0. Now look at the exponent part, which is the power of the radix 2. In this case, it is minus 2, which can be expressed in excess 127 bit pattern as 0111101. Now we combine the three parts together. Then the 32-bit single precision bit pattern for 0.34375 is this bit string. Hope this gives you some idea on how computers represent floating point numbers. We will look at more examples in other videos.